All right, so let's continue with our with the question that how do we design more complicated gates? So we started our discussion with CMOS two-input NAND gate, the schematic of which is shown over here, and the issue that we were addressing is how do we determine the size of the NMOSs and the PMOSs? And with that question in mind, what we said was let's look at the inverter that we had designed. And for the inverter, we had chosen the minimum NMOS size, 4 lambda by 2 lambda, according to the rules that we are using. And to balance the currents of the NMOS and the PMOS to make them comparable so that we get a symmetrical VTC, delays are also comparable. We had chosen this as 8 lambda by 2 lambda. So this was the design of the inverter that we had obtained. And we had called this design as 1x inverter of strength 1. And we said that we can make a 2x inverter by doubling the size here, and by doubling the size here, that would become 2x, and then 4x, and 8x, and all that here. Now, this is not a unique design. It may happen depending on the values of Kp and Kn. Somebody may keep here, that was the homework problem, somebody may keep 6 lambda by 2 lambda here, 8 lambda by 2 lambda. So there are different possibilities. I'm just pointing out one of them. Okay, so the 1x inverter that you see here may differ. Somebody can even design, let's say 1x inverter, may call it 4 lambda by 2 lambda here and 4 lambda by 2 lambda here also. Let's say both of them. The currents are not balanced, VTC will not be symmetrical, the delays will also be not symmetrical, but if it's okay, you know, if you can live with it, that's also fine. So there are various possible ways in which I can design my inverter. This is not a unique design. This is a freedom that I have, and we took it as minimum size here. And again, if you look at it, why did I choose minimum size? Well, maybe the thought behind our minds are that if you choose a minimum size transistor, the areas are minimum. The areas would be small. But we know that, if you do a quick layout, if you go from 4 lambda by 2 lambda to 6 lambda by 2 lambda, the areas do not increase much. The areas do not increase much as you go from 4 lambda to 6 lambda here. The areas do not increase much. And the capacitances also do not increase much. So then why just use a 4 lambda by 2 lambda? Why use a minimum size? It defeats the purpose because, as I said, at the back of our minds is small transistor, a small size that you see here means a smaller layout, smaller capacitances, but it may not be. The difference between 4 lambda here and 6 lambda may not be very strong. And when you go to 6 lambda, the current drive capability of this transistor or the drive strength of this transistor improves. Okay, it may not be very symmetrical. If I use 6 lambda here and 8 lambda here, may not be very symmetrical. You may compromise a little bit on the noise margin, but it doesn't matter. This system, provides you with enough noise margin to begin with. And therefore, that may be a viable design also. So I may have a 1x inverter with this 6 lambda by 2 lambda and this is 8 lambda by 2 lambda. That's also a viable 1x inverter here. So what I'm pointing out is not unique. That you should always say, if I'm going to design an inverter, 1x inverter is going to be 4 here and 8 here. Need not be. You can make choices. You can make here 6 and you may make here 6 also. 6 lambda by 2 lambda here, 6 lambda by 2 lambda. That's also fine. Okay. Unless somebody specifically tells you, I want a perfectly symmetrical VTC. Or I want the propagation delay low to high and high to low propagation delays to be very close to each other. If certain constraints are given to you, you have to design it that, maybe you'll arrive at a unique design. But if those constraints are relaxed, VTC may be a little bit towards the right or a little bit towards the left. If the constraints are relaxed, if the constraints on propagation delay, that the two delays, high to low and low to high, may not be exactly balanced, then you have a freedom here. You have a freedom here in terms of what ratios and all that you can choose. Okay? So please keep that in mind. Although we are calling it 1x inverter, there may be several other designs which may be possible. So with that in mind, and there are several designs possible for the NAND gates and all the other complicated gates here. So our thinking was that if I take this 1x inverter, what we would like to do is size this particular NAND gate such that under worst case condition, the strength of this particular gate is the same as the strength of this gate. Now strength in what? Strength we are talking about is ability to charge up a capacitance, a load capacitance here. So we are talking about strength of a, let's say the pull down network Pull down network is here. We are talking about the strength of a pull down network in terms of how much current can it provide. All right, because whatever load capacitor is attached here, whatever load capacitor is attached here, the delay then depends on how much current I can supply. Right, so strength is being talked about in terms of how much current can this supply here. And then the current, of course, you need to look at under what condition should I look at the current here and here. All right, so the thought is then design the 1x NAND gate such that under worst case condition, it has the same drive strength as 1x inverter. All right, so that's that. With that in mind, we are designing that this should have the same strength as this particular one. Now, same strength under worst case condition. If you look at the worst case condition for a pull up network is when only one transistor is on. Right? It's possible that both of them are A is going from 1 to 0 and B is also going from 1 to 0, and therefore both of them turn on simultaneously. And whatever capacitance is there, both of them charge it up. But more common you would realize is that either A is charging or B is charging. Simultaneously, both the input switching is much more rarer event unless you short them together for some reason, if you tie them together. Otherwise, it's more rare that both of them are switching at the same time and in the same direction, 0 to 1 or 1 to 0 and 1 to 0 here. So worst case condition for pull-up network is either this transistor A is charging my capacitance or transistor B is charging my capacitance. Right? If I want to maintain the same strength as this, well, the strength of this is because of size 8 lambda by 2 lambda. So it's obvious under worst case condition, I should choose the size here of PMOS also 8 lambda by 2 lambda. Then under worst case condition, it has the same drive strength as this. So that's rather straightforward. How do I choose the size of PMOSs? Just choose it as 8 lambda by 2 lambda here, both of them. The size of the NMOS is a little bit more complicated. So remember, we are looking at the size from the viewpoint of delay, drive strength. So delay, now note that if I look at pull down, how should I look upon delay? Well, typically what would happen is to pull a node to ground, both the inputs would be high. Then only you'll be pulling it to ground. And if we consider abrupt inputs for simplicity, both the inputs are high, which means there is VDD here and there's VDD here. Right? So when I'm pulling a node down, the condition that I'm in is I have these two transistors with both VDD here and VDD here. And under that condition, I want to make sure that the current that flows here is similar, close to the current that flows in this case. Okay? So with that in mind, we had shown this graph here. This diagram here. Right? So if both transistors, all transistors are 4 lambda by 2 lambda, this is my inverter's pull down, and this is my NAND gate's pull down network here. VDD to both the inputs. And if I compare the two currents here, the two currents came out to be 546 and 236 here. I can do analytical calculations also. With some effort, I can see here that one transistor may be in saturation, other may be in linear and all that. And with some calculation, we can calculate this. But these results are from simulation. So 546 here and 235 here. So what it says is if you choose these two transistors as 4 lambda by 2 lambda, the current in this particular branch would be roughly half of this. When this particular node is 3.3, right? It's half. So if you want to balance the current, then you would say, well, let me make this double the size of this one. Double here and double here would then end up giving me double of this. So will end up giving me around 470 or so, and which is close to 546. So to balance the current in these two conditions, I would want this transistor and this transistor to be double the size of this particular one. This is when the node is at 3.3. Note that capacitance is attached here, 3.3. But as the capacitance discharges, it goes from 3.3 to eventually 1.65. 1.65 is where we define as tau p HL limit. So if you look at when the output is 1.65 also, if you look at the two currents here, 494 and the current is 223. Again, about half. So if you would like to maintain again the same current here as a current here, what we are saying is we may have to double the sizes of both of them. So with that in mind, our design then becomes the following. Our design becomes, this we said is 8 lambda by 2 lambda here, anyway PMOSs, and then we choose 8 lambda by 2 lambda and 8 lambda by 2 lambda. With these two, with this size here, the pull down network will have a same or similar. It was not identical. Please go back and see the currents. It will not be identical, but it comes close to the drive strength of this particular one. All right. So with that in mind, we choose these as 8 lambda by 2 lambda and 8 lambda by 2 lambda. So that sort of completes our design of our inverter. Design of a, what we'll call this as a 1x NAND gate. NAND gate of strength 1. Right. So because the currents here and the currents here are similar, again current here and the worst case is same as current here. So its ability to charge and discharge the capacitance is the same. So 1x NAND gate becomes this. If you want a 2x NAND gate, well, you will have to double all of them. You'll have to make this 16 lambda, 16 lambda, 16 lambda here and 16 lambda here. So that would become a 2x NAND gate. All right. So, all right. Now, once you design this gate in this particular manner, let's evaluate this particular gate. All right. So we designed this particular gate keeping in mind the delay. We are sort of balancing the drive strength. So let's go back and see for this design what happens to the VTC. Noise margins are important, voltage transfer characteristics important. So let's look at the VTC under this design now. So this is what this diagram shows here. These are now design of the NAND gate. And VTC, we can measure VTC of this one under 3 cases here. Case 1, case 2 and case 3. Case 1 is when note that B is high and A is the one which is switching. A is where, so your input is A and A is over here. Right? So that's case 1. Case 2 is when A is permanently connected to 1 and B is making a transition. You're going from 0 to 1, so you're doing that here. That's case 2. And case 3 is when we tie A and B together. A and B, all these are tied together, which means simultaneously switching of both the inputs here. So that's case 3. And for reference, we are keeping this inverter here. There's a reference design here. So the reference design was pretty balanced and its VTC is shown in black here. VTC is shown in black that you see here. The inverter threshold voltage is very close to 1.65, ideal VTC for this case here. Now, for the NAND gate, case 1, case 2 and case 3 are shown here. Case 1 is here, case 2 is here and case 3 is here. None of them are in the middle. Why? Because remember we designed our NAND gate with delay in mind. We were keeping pull down strength and all that. We didn't design it and note that it's not possible to keep VTC in the middle because there are 3 VTCs. There is 3 and there is 1 and then there is 2. There are 3 VTCs. If one of them, let's say if I push here 2 and make 2 come towards the middle, then 1 and 3 will go towards the right. So it's not possible to have a VTC right in the middle because we have different conditions. Okay, so it's now it's possible that all right. So do we understand why these VTCs are shifted in this particular manner here? So if you note 3, why is 3 shifted towards the right of my inverter? So note that compare the inverter with the 2 input NAND gate, right? So we are looking at case 3. Now case 3. No, please keep in mind, why does the VTC shift towards the right? It shifts for 2 reasons. Either my pull-up strength is high, that pull-up means it's maintaining it to a high level. Pull-up strength is high, or my pull-down strength is low. These are the 2 reasons which shifts the VTC towards the right. Now here, if I compare with respect to the inverter, note that the size of each transistor is 8 lambda by 2 lambda, and I've connected them in parallel. So effectively, I have 2 transistors pulling my node up. And 2 transistors in parallel are like one transistor with a size of 16 lambda by 2 lambda. So pull-up strength has definitely increased as compared to the inverter. And that's why it's shifting. What about the pull-down strength? Well, when I have 2 transistors in series, like this here, both of them shorted together, and we are looking at voltage here. Note that for VTC, we are looking at voltage at this particular node around, let's say 1.6, and the voltage around at this point is 1.6. We are looking at roughly in the middle, okay, the voltage levels here. So when you look at voltage levels here, let me show you what happens to the transistors here. This one, and this one here. Under a different condition now, note that voltage here would be around 1.65 and we are keeping voltage 1.65. While under discharge of a capacitance, we kept this as 1 volt and the voltage here was initially, 3.3 volt, and the voltage was 3.3 and then 1.65. So it's a different condition here. This is a chart that we have shown earlier. When you look at two transistors, both of them are shorted together like this. Both of them 4 lambda by 2 lambda here. Then the current here is 18.35 compared to 43. So we are looking at, remember, we are trying to understand case 3. So case 3, we have already seen pull-up strength is twice as this one. So it will shift. What happens to the pull-down? Well, let's look at pull-down here. Two transistors in series here, and with both of them shorted together, the current here is 18.35 compared to 43, roughly, let's say, half. When the sizes are the same. But in our case, the size of this is 8 lambda, and size of this is 8, while this is still 4. So this will become double here. So this will from 20 to really 40. But still, pull down is not as close as to this one. So if I go back to this and I try to understand here, the pull down strength of these two transistors is a little lower than the pull down strength of this. And the pull up strength is become doubled as this. And for that reason, then this has gone to so much towards the right. Right? And so if you're wanting to find out how do I let's say estimate what is the threshold voltage for inverter threshold voltage, it's acting like an inverter. What is the inverter threshold voltage for case 3? Then what I'll do is the expression that we had for an inverter, we can use it here also, approximate same here, except that the size of the PMOS will be no longer 8 by 2. We will make the size, this is equivalent to 16 by 2. And these two together, connected in series, they are equivalent to a transistor of similar size. Note that currents are, if I double it, this will be around whatever, close to this. So an approximate value for the threshold voltage here we can obtain by replacing these two series transistors as one single transistor with the same size as 4 lambda by 2 lambda. So NMOS remains the same, and PMOSs, two PMOSs will replace by 16 lambda by 2 lambda. We'll take that, we'll put it in our expression, and you'll get a value for the threshold voltage at this particular point. How far to the right it has moved. Now, case number 2 is also relatively easier to tackle here. Case number, note that my VTC lies between these two extremes. 3 is the other extreme, and 2 is the other extreme. 2 is the leftmost one, and 3 is the rightmost extreme here. So 2 is also relatively easier to calculate because look at the case 2. Case 2 is what? When input A is connected to VDD and B is what is switching. B is switching here. Note that since A is connected to one of the PMOS is inactive. So effectively I have only one PMOS available here. So the pull-up strength is same as pull-up strength here. So that's this thing here. Pull down, if you look at, I have this transistor permanently on, and this is what is switching here. So let's look at the current here in this one. So go back and look at case number 2. Case number 2 is this one. Case number 2 is this one. Right? So now in the diagram that I'm showing is where all transistors are 4 lambda by 2 lambda. So if you compare 43 here and 42 point, almost 43 here. But when they are of the same size, we have actually done what? We have made this 8 lambda and we have made this 8 lambda. So the pull down current for us will become 84 or so. So pull down current has increased compared to that of an inverter. Okay, so effectively in this condition, what is happening is these two series connected transistors are acting as if it's a transistor of the same dimension as this. Because the currents are similar. 43 here and 42.76 here. So two series connected transistors are as if they are same here. Why? Because there's VDD connected here, a large bias connected here. So this has very low resistance. The transistor is in saturation region and I have 1.65 here roughly. So it's acting as like this here. Now, because we have doubled the size here, so this will act like a single transistor of size 8 lambda by 2 lambda under this condition. So you can again calculate how far to the left has this gone by looking at this condition. This is only 8 lambda by 2 lambda, one transistor. And these two together will act as a single NMOS transistor with the size 8 lambda by 2 lambda. also. Single transistor with 8 lambda by 2 lambda. And with that, you can find out what is the threshold voltage again, which will give you this one. Case number 1 is more complicated. See, the current is 31.1. It requires more. You can't simply replace the 2 transistors by 1 transistor with either double or the same size here. It's more complicated here. It requires more analysis here. But these two, so first of all, you should understand, why do I get these 3 VTCs? Why is this towards the rightmost extreme? Why is this 2 towards the leftmost extreme? Why is 1 somewhere here? You should understand, and these are based on these currents here. Which transistors in linear, which transistors in saturation. Based on that, you can see why the characteristics are shifted towards the right or the left here. Okay. So that's as far as the VTC is concerned. Once we have the VTC, remember we have V inverter. We can these are all simulation results, but you can calculate it, at least for these 2 cases here. 2 extreme cases you can calculate. And VIL and VIH are, as I said, slightly displaced to the left of this. VIH is slightly displaced to the right of it, and roughly maybe somewhere between 0.1 to 0.2 volt shifted towards the right or the left here. Okay, so for our quick analysis, we'll take that the VIL is shifted left of V inverter by about 0.15, and VIH is shifted to the right by 0.15. We'll roughly take that particular value, but you can see here it's not exactly 0.15 here. If you compare VIL and V inverter, it's 0.18, and if you compare 1.72 versus V inverter, it's also not exactly that. But for a quick calculation, the shift is roughly between 0.1 and 0.2. Okay, so we'll take some average of 0.15. So whenever you are asked to calculate in exams and elsewhere VIL and VIH, what you do is you calculate V inverter, and then you add plus 0.15 and minus 0.15 to get VIL and VIH, approximate values. And once you get VIL and VIH, then of course you get the noise margins. All right. So this is how we end up getting the noise margins here for our design here. So let's come back and then let's look at the delay part here. So delay for this design. So the first thing that I did was, these are the 3 conditions under which again I can look at delay. They may turn out to be similar. Okay, so these are the 3 conditions under which I can look at delay. And most of the time, as I said, this condition is not really discussed much. Why? Because it's more as I said, unless you tie the 2 inputs, all the inputs together. And when you tie all the inputs together, it's no longer a NAND gate, it is an inverter. And why would you make an inverter in this complicated manner? You have a simpler inverter available, so why would you not choose this and use a much larger design here? So you won't actually tie up all the inputs together. Normally you won't do that. And effectively, if you're wondering that they're effectively tied because they're making transitions at the same time, so that's a more rare event. Both the inputs are making transitions 0 to 1 or 1 to 0 simultaneously, is a rare event. So this is normally not discussed much. So when I'm looking at a NAND gate, what is discussed is that this is a 2-input NAND gate. One of the inputs is 1. One of the inputs is permanently high, let's say 1, and the other input is making a transition. So either this is making a transition, or this is connected to 1, and this is making a transition. In more complicated NAND gates, if I have a 3-input NAND gate, what we'll say is in 3-input NAND gates, A, B, C are the 3 inputs, B and C are at 1, and A is making a transition. Or A and C are 1, B is making a transition. Or A, B are 1, C is making a transition. So we look at these 3 cases here. And in this case, we look at these 2. So we need to look at delay under these scenarios here. And so, first of all, a very simple case, what I did was I took these inverters. We have the size 8 lambda, 8 lambda, 8 lambda, 8 lambda. All the sizes are here. This size is separate here. So what I did was I just took a 20 femtofarad a capacitor and just attached at the output of each one of them. There are no other capacitors present, let's say. I just put 120 femtofarad capacitor here, 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 and here to all of them. All right. And then looked at, well, the delays. This is not a realistic picture of delay. Remember, capacitors are here and somewhere else also. But, so when I put here 120 femtofarad capacitor here, all that I was trying to see is that under transient conditions, the pull down strength and the pull up strength. so when I have a lumped capacitor here, is discharge would be depending only on the pull down strength here and pull up strength here. So if you look at the pull down, you're pulling the output down. This case, they're all similar. Note that they're almost all together here, and it's equivalent to the inverter also. Note that all of them are here. Inverter, everything, all that you see here is all of them are shown here. They all pile up, and it's not a wonder that these are all pull down. All are coming together because we sized these ones such that the strength of this one is the same as the strength of this one. Right, so we size them in that particular manner. That's why they're all coming at the same point. Okay, so they're all pulled down in the same manner here. Note that when I'm switching it on, even though this is B is 1, I'm switching, when I switch A, I'll abruptly switch it to 1 also, which means VDD here and VDD here. Similarly, when I switch it, there'll be VDD here and VDD here. So the two are equivalent under switching. VDD here and VDD here also under delay. And similarly, when I switch this here from 0 to VDD, there's a VDD here and VDD here. So all three actually become equivalent. That's why they all, together. Pull up, all two of them here, and this one inverters are all together here, except for this one. When I pull it up, because two of them are in parallel, so effective size is 6 lambda, so it charges up much faster here. Anyway, so all this example illustrates is that we size them properly. We size them such that the pull down strength is 1x as like this one. This example is only showing that. Now, to actually estimate delay, we have to put properly capacitance. I can't just take a 20 femtofarad capacitor arbitrarily and put it here. What capacitor to put and all that, we have to get it from our, by looking at all the drain, body, all those capacitances here. So for that, the first thing that we need to do is the layout. We need to do the layout of the NAND gate. Again, there are many ways in which you can do this, not an optimal layout. This was done in couple of minutes. So you can see here is more twisted. It need not be like this. It need not be in this complicated manner. But you can see I have two NMOSs in series here. There's one NMOS and there's the second NMOS here. Note that this the input A. This is the upper NMOS which is connected to the output here. This is the output line here. So this is the upper NMOS, this is the lower NMOS. And upper NMOS we are calling it input A, lower one we are calling it input B. So that's the two inputs series connected, and these are two parallel connected PMOSes. And this is the output which is taken from here. Output are shorted together. Alright, look at the areas. The areas which are relevant for us is, this is the areas, if you go back, I need to calculate capacitance at this node. And capacitance at this node requires, one of the contributions that you are saying, this is the drain of this PMOS and the drain of this PMOS. So I need to know the drain to body capacitance. So the drain, note that drain of both of them are common. Drain of both the transistors are common, and this is where the drain is. And so by looking at it, I calculate the drain area drain and perimeter drain. Alright, so this will help me in calculating the capacitance coming from the drain here. The other one is the capacitance at this node comes from drain to body of this one, A. And A is here, input A is here, this is the drain to body capacitance. This is the area that I needed for that particular part. The other capacitance that I need is in the middle here. At this internal node, there will be capacitance coming from drain to body here also. Right, drain to body, this part here. So I need the area of this particular part here, this small area. This area, note that this area, the source and the drain are shared together of the two NMOSes, okay? So this happens to be the drain of the lower transistor, and this also happens to be the source of the upper transistor here. So this entire area is needed for drain to body or source to body capacitance here. So this is what is needed here. So all the areas, once you do the layout, you have this area, you have this particular one. These three relevant areas are there, which can be then used to estimate the capacitance here. Now what I want to show here is the difference between the NAND gate and the inverter. This is our inverter, right? Inverter is shown here, 8 lambda by 2 lambda and 4 lambda by 2 lambda. And this is our NAND gate here. Just take a look at the areas. No, again, note that if we look at 8 lambda by 2 lambda, what is the drain area? Drain area is 50. Let's just look at 50, and perimeter is 22 in this case, right? 50 and 22. When I have 8 lambda by 2 lambda. When I connect two transistors in parallel, a simplistic analysis would tell you, well, each one of them would contribute the same drain to body capacitance, right? But what is the effective drain area that I calculate? 64 and 16 here. Note that 64 and compared with 50, it doesn't double. 64 and 50 doesn't double. Okay, so that's the first thing. Areas are not simply doubling. I've connected two of them in parallel here. The area didn't simply increase to 100 here. And in fact, the perimeter here is 16 and the perimeter here is 22. So perimeter is a little smaller here. There's a sharing of this thing here. So it didn't double. The other part was, look at the NMOS. The NMOS is area here. The NMOS is area. This is 4 lambda by 2 lambda. The NMOS area is 40. Now in the PMOS, in the inverter, the NMOS is area has, we made the size 8 lambda by 2 lambda. Look at the drain area here. Drain area is 56 here. So again, this area is 56 compared to 40, even though we have made the size almost double. All right, so it didn't increase that much here. The internal node here, this is a fairly small area here. Note that in between the two here, the area is not very large here, 24 and perimeter here. Right, so if I don't do the layout and simply look at this particular point, I would say, well, there is a this is source, so I will get source to body capacitance of this transistor, and this also happens to be the drain, so I'll get a drain to body capacitance, and as if I'm getting a very large capacitance here. The capacitance is not that large here, because this area that you see here is not that large here. Okay, so anyway, layout helps you to understand how the areas scale, and so we need to get all these values here. So let's come back and look at the propagation delay. So with the layout, we know that we have all the areas with us, and we can potentially estimate all the capacitances here. So this is our NAND gate, and what we are doing is we are taking a inverter as a load for a NAND gate. And so what we'll do is we'll examine the delay under this condition. Let's say this is permanently connected to 1 first, and this is the node which is switching. And if we try to lump all the capacitances, I end up getting two nodes here, two nodes which are important. One is this particular node. We lump up capacitances here, and one is an internal node. We need to lump up capacitances here. So this node, you can see here, the capacitances will come from this is the gate and the drain, gate drain of A, gate drain of this transistor, and then drain to body of this transistor, drain to body of this transistor. These are the capacitors that this contributes. Similarly, this one, there's a drain here and drain to gate of this one, and then drain here and body is connected to ground, so there's a drain to body of this one. So these are the capacitors that contribute here. When you look at this one, the capacitors at this particular point come from gate to source. There's a gate and source here, and there's a gate and drain here of this one. So gate to source of this one and gate to drain of this one, plus the drain to body and all that capacitances. They will all add up to give you CT2. So if we do that, we have done these calculations. Once we have the areas and all that, we can do approximate calculations. What it ends up is about 21 femtofarad here and 6 femtofarad here. Capacitance here, roughly. These are very rough values because they all change with bias and other things. So 21 and 6. If you recall, what was the capacitance of the inverter at the output? Was around 20 femtofarad. So it didn't increase that much. Even though I have a more complicated NAND gate, and its load is this inverter, the net capacitance at this node is only 21 femtofarad. In the previous case where I had this inverter and one inverter was driving a similar inverter, all I had was 20 femtofarad. Didn't increase that much. Okay, why? Because you saw areas and all that are not increasing that much. Okay, but what we have is an additional internal node which is 6 femtofarad. There's an internal capacitance that has come apart from the output capacitance here. Now, This is interesting, this condition. Why? Because you note that I've applied permanently 1 here. Permanently 1, which means VDD here. So this is ground, this transistor is on, so this is 0. And so this capacitor is always discharged, CT2. So even though it is there, under this condition, it will not matter. Because as you switch A, as A goes from low to high, all that you're doing is, when it was 0, this node was high, and when you make it 1, this node is pulled down. But nothing really happens to this particular node. It stays 0. So this capacitor is there, but it doesn't matter. All right? And how do we estimate the delay? Well, the delay estimation is given here. 0.5 CT1 VDD by pull down. So this is the capacitor that will put 21 femtofarad, VDD we know. And pull down current, well, note that when I switch it on, I'll make this as VDD and this as VDD. And we know under this condition, the current of this one is just like the current of a 4 lambda by 2 lambda. So we know approximately how to calculate the currents, and we can obtain tau PH. We get a value of 79 picosecond for this one. Okay. The other condition is more interesting. The other condition is where this is 1 and this is switching. Now note that when B is 0, which means this is 0, when B is 0, so output is high, so this is charged to VDD, and the output, this transistor is on, so the output is also, this node is also connected to VDD through this transistor here. Okay, it may not reach exactly equal to VDD, because note that if this is VDD here, this node will not reach VDD under reasonable time scales, because the moment this reaches VDD minus VTHN, the transistor sorts of cuts off. So it will be charged close to VDD, but not really exactly VDD. But anyway, so this node is also high and this node is also high. When I make B equal to 1, I switch it on. Now this capacitor has to be discharged and this capacitor also has to be discharged. So I need to discharge 2 capacitors here. So the delay is going to be higher. If I discharge this capacitor, well, CT1, VDD, IPD1, whatever is the current that is discharging this one here. When I look at this one, well, this is a very simplistic analysis, 0.5 CT2, whatever is the pull down current associated with this. So as a very crude analysis, we can take this capacitor, 6 femtofarad here. We can initially note that this is close to VDD, this is VDD, transistor is in saturation region, and we can calculate what is the current here. And put that current here, and sort of get an estimate of this one. And similarly, get a current in saturation for this one, and you can put it here and calculate. So point is, the delay here comes out to be higher, 94 picosecond. So compare this, when when the lower transistor is switching, I have higher delay, 94. When the upper transistor is switching, I have a lower delay, 79 picosecond. And what is the reason for it? The reasons that you see is the internal node capacitance. This also has to be charged and discharged. Okay, so the 2 inputs to the NAND gate are not equivalent. The lowest one, if you switch, always gives you the highest delay. The upper one will give you the lower delay, right? So, which also tells you that if there's a NAND gate in your critical path, if there's a NAND gate in your critical worst case path that we saw here, and where should you put that input? You should try and put that input, whichever one is there, the critical input, you should try and put it here. Don't put it at the lower one. The lower one will add more delay, right? The 2 inputs are not equivalent. That's an important point to keep in mind. I'm showing it for tau p high to low, similarly for low to high also. If if B were, let's say, so in this case I said is going from 0 to 1. But what if it's going from 1 to 0? If it's going from 1 to 0, please note that this capacitor will have to be charged and this will have to be charged to VDD. So 2 capacitors have to be charged. And therefore, the tau p LH would also be high in this case. Both will be high here. Okay. So you can see the comparison here. These are actual delay values. This is for 180 nanometer, not for our design, 180 nanometer. And I don't know how they've designed, by the way, how they've designed the NAND gate. That information is not available. How did they size the transistors here? How did they size the transistors here? I don't have any information, but we are just comparing. So you can see here, if you look at input A and B. So A is the upper input and B is the lower input here. So if you look at the delay, when A is being pulled down, 0.017, and when B is trying to pull down, 0.021. So you clearly see that B is slower than A. B intrinsic delay 0.021 versus 0.017. B is slower than A. Not only that, when A is pulling it up, when A is pulling it up, I'm getting 0.027. When B is pulling it up, the node, you get 0.034. So B is slower. The input B, the lower input, is a slower input. If you put a signal there, it's going to go through the NAND gate with longer delay than if you put the input here. It will go through the NAND gate with lesser delay A here. All right, and then of course there's strengths and all that is there. Okay, so let's so that's as far as the delay values are concerned. As I said, calculation of exact delays become a little bit of a problem because the calculations of the currents, the moment it becomes 2 transistors and 3 transistors, current become a little bit messier to calculate. So that's delay. So we've looked at VTC, we looked at the area of the NAND gate. We just looked at the delay. The next thing is the power dissipation. So the power dissipation, again, we are ignoring the static power dissipation, looking at mostly the dynamic power dissipation. Dynamic power dissipation is associated with switching of a node. And if a node is switching at a frequency F, and the node has a capacitance CT, and is switching between these two limits, 0 to VDD, that's the power which is dissipated. Otherwise, if the node is not switching at the same rate as the clock, then we add a what we call as the activity level, alpha here. So activity level, which is number of transitions that the node undergoes per clock cycle. Okay, so that's the number of transitions that it goes per clock cycle here. So if I look at a NAND gate, we have 2 nodes which are potentially switching, this one and this one. So the power dissipation for a NAND gate, under this condition, if you look at, when you put a 1 here and this is switching, node A is switching. So since this is 1, CT2 is always connected to, is always discharged. So this does not contribute. The only power dissipation comes because of switching of this one. So it's F CT1 VDD square. On the other hand, when you're switching this, B, then you have contribution from CT1 F VDD square and then CT2 F VDD square. Note that this particular node does not really switch between VDD and ground. So this is an approximation. It will switch, as I said, this particular node will not be able to reach VDD under normal time scales. You know, it may only reach about VDD minus the threshold voltage. All right, so more accurately, one may write here as VDD minus VTHN square. So that's the power dissipation. So note that in both aspects, input A is preferable. The signal being applied to A is preferred than signal being applied to B, because A is associated with lower delays, and A, when you switch this, is also associated with lower power dissipation. Lower power dissipation here as compared to power dissipation here. So A is a preferred input in a NAND gate as compared to the B here. Well, what about the 3-input NAND gate now? What will happen in the 3-input NAND gate? So I have 3 of them in parallel, 3 of them in series. Now how do I size them? What is the principle? One of the principles that we've been following, look at a 1x inverter. Look at a 1x inverter, size the NAND gate such that it also has a strength of 1x. Okay, so what do I do? Does everybody see what should I do to the PMOS? Under worst case, only one of the gates is, one of the transistors is active, so make it 8 lambda by 2 lambda. Right, so PMOS is a straightforward. 8 lambda by 2 lambda, make each one of them 8 lambda by 2 lambda. Now the issue is, what do I do with these? Now our idea was that, remember, our idea was that we should size them in such a way that the strength of this pull down network is same as the strength of this one. Alright, so to do that, I need to look at current here and the current here in these. And this is a picture which will tell you. Now, you know, we may soon, if we wish to talk about 4 inputs, so I've put 4 of them also there. So you can see all the currents. All transistors are 4 lambda by 2 lambda here. 0.4 milliamperes here, 2 of them 0.23, 1 of them 0.15, and 4 of them 0.11. This is at 3.3. All the inputs are at 3.3 VDD. Now, note that when I'm discharging my capacitance here, all the transistors would be VDD. This will be VDD, this will be VDD, this will be VDD, and initially the capacitance node will also be VDD. I'm discharging it from VDD to 0 or VDD to 1.65. So this is one condition which is of interest. The other condition which is of interest is where this node has reached to 1.65. Again, this is VDD here. So this is 0.49, this is 0.22, 0.14, 0.106. So how should I size? Let me go back to the previous one. How should I size these ones? I want the strength of this one to be same as strength of this one. So what should I do? Right now, all the sizes are the same. So what should be the size of this one? Well, let's divide 0.54 by 0.15. That is 3.6. And 3.6 into 4 is 14.4. Right, so what should I do? The sizes here become maybe 14 or so. The sizes here. And if I go to a 4-input NAND gate, this is 0.11. And 0.54 divided by 0.11 is 4.9. 4.9 into 4 is 19.6. So if I try to balance these same, I'll have to make this each 20 lambda by 20 lambda here. So this is getting into a problem. The transistor sizes are becoming large, their capacitances would become large, and so you're saying 20. If I had 5 of them in series, the current would have fallen even further. You may have required, I don't know, maybe 30. So very rarely you would find anybody would make more than a 4-input NAND gate. You're seeing why this is happening. To balance the strength, you're seeing the transistor sizes are becoming 15 here and 20 here. Transistor sizes are becoming larger and larger. All right. Why? Because now, if you don't want to make this transistor size larger, well, I can keep these at, let's say, 8 lambda by 8 lambda, 8 lambda here. So what would happen then? It won't have enough current, and therefore its drive strength reduces. It will not be able to charge and discharge capacitors as readily as the inverter. So you will start incurring delay penalty. So we have a choice now here. We have a choice here. We can make each one of them 15 lambda or 14 lambda and do the design. But I've not gone through all of them. Now you need to see the other things also. These are now, look at, so this is as far as the currents are concerned. Now look at 3 different conditions for delay. When input A is switching, when input B is switching, and input C is switching. And I've shown you all the capacitors now. This is the normal node here, output node, there's a capacitor here. 2 internal nodes are here. 2 internal nodes here, 2 internal nodes here. Which one would be the fastest or the smallest delay? The top one. Everybody sees why? Top one A, note that this is 1 and this is always connected to 1. These capacitors don't matter. They don't matter at all. In this case, this is permanently connected to 1. This capacitor doesn't matter. In this case, all capacitors matter here. So the delay is going to be highest for C, then for B, and then for A. Right? And now we'll have to do the layout to figure out how much is the capacitor here, how much is the capacitor here, and then look at all the currents and all that and analyze what happens to the capacitor values here. So if you want to see NAND 3, you can see all the delay values for NAND 3. You may focus on A, B, and C. You can look at the delay values. So say A is 0.024 here, B is 0.031, and C is 0.033. But what is worse is actually not the pull down, but pull up. So pull up is 0.034 when A is pulling it, 0.043 when B is pulling, and C is 0.051. So the worst case delay is the pull up delay here when you're pulling a node up, which means that what is happening is worst case is occurring when C is switching and C is pulling, so you're going from 1 to 0. You're going from 1 to 0. So this transistor has to pull this capacitor up to VDD, has to pull this capacitor up to VDD. Now to pull this capacitor up to VDD, the current has to go via this one, via this particular transistor, so it has to go through this. To pull this up, it has to go through this, this, and this. And therefore, the current available for pulling this capacitor up is small, because it has to go through these two, through this path here. The current available for pulling this up is a little bigger here, and for this is a little bigger here. So the worst case delays are coming out when you have to pull a node up, and you can see here 0.051 or so. All right, so again, I'll leave it for you to look at NAND 4, what is happening here. But as I said, we basically stop at NAND 4. You won't find people making NAND 5 and NAND 6 and all that, for the reasons that you see in this particular case. So either the drive strength goes down, or the sizes become very, very large. So both ways you start suffering. Okay, so you don't do that. Plus noise margins, you can begin to see what would happen to the noise margins. In this case, how many VTCs will you get when I have 4 inputs? So try and draw, maybe in the next assignment we'll ask you to do that, how many different VTCs and where they are.